All right, let's take a look at the questions from Checkpoint 10. So question one deals with some data from hospitalizations with from COVID-19. All right, so we're asked for some probabilities of some specific event spaces here. So part A, what is the probability that a patient was younger than 65 and vaccinated with or without a booster? Okay, so we have a compound probability. So let's identify those individual sets, and then we can figure out exactly what we want. So younger than 65. So who are those people? These people are anything in the top two rows, right? So patient was younger than 65. So we have that here. And vaccinated. It does not, so, and vaccinated with or without a booster. So I wish I had different colors, but I don't. Or do I? I haven't thought about that. Oh, okay. So blue is the people who are younger than 65, and red is going to be the people who are vaccinated. So now that I've identified both sets, how do I bring them together? So operative word here is and. So I want the intersection of those two sets. So the probability that a patient was younger than 65 and vaccinated without a booster. So let's add all those people up. That's going to be 214 plus 59 plus 358 plus 151 all over. So this is our event space, the numerator here. And our sample space has how many people in it? That is 10,125, which I'm getting from the very lower right corner there. So quick calculation. 214 plus 59 plus 358 plus 151 divided by 10125. I am getting a probability of 0.077. Okay, so that was part A. Part B, what's the probability that the patient was younger than 65 or vaccinated? Okay, so these are the same two sets. Younger than 65 or vaccinated. Except now the thing that's joining those two sets is or. So this first question was dealing with the intersection of those two sets. The second question is dealing with the union of those two sets. So typically the way I would find the cardinality of this event space, I would add the cardinality of the blue set plus the cardinality of the red set, and then subtract the cardinality of the intersection. But what I can do instead is let's just add in the cells that I didn't already add before, because the intersection is going to be included in the union. So now what's left? Plus 2,850 plus 3,246 plus 491 plus 277. And the sample space is still the same here. So let's do a slightly less quick calculation. 214 plus 59 plus 358 plus 151 plus 2,850 plus 3,246 plus 491 plus 277 divided by 10125. Much higher probability of 0.755. All right. Okay, so that's part B. Part C, what's the probability that a patient was at least 65 and unvaccinated? So I'm gonna go ahead and clear the deck here because I'm not dealing with the same set anymore. the probability that a patient was at least 65. So we got two sets again. Let's go ahead and identify them separately, at least 65. It's just this row. And unvaccinated. So let's identify the unvaccinated part of the sample. And I care about the N. So I'm looking specifically at one cell, basically the intersection of those two sets. So my probability is 2479 over 10,125. Much faster calculation. 0.245, 0.245. All right. Part D, kind of at first blush, seems like the same question. But is it really just one word? Nah, more than one word. But what is the probability that a patient who was at least 65 was unvaccinated? So this is going to be different. So, I mean, linguistically, the way that's written is not much different from the way that Part C was written. But mathematically, this is going to be a pretty big difference. So for Part C, what was the sample space? The sample space was this whole population. So my denominator was that cardinality, 10,125. But here, what is the probability that a patient who was at least 65 was unvaccinated? So the way that's worded, it's subtle, but now I'm not looking at this whole sample. I'm only looking at the 65, the people who are 65 and older. So now this question is restricted to this, totally restricted the wrong thing. This question is restricted to the bottom row here. So what's the probability that a patient who was at least 65 was unvaccinated? So first, let's identify the event. Basically, the numerator of this probability. I think it's the same numerator as before. I want 65, somebody who's 65 or older, who's unvaccinated. That's 2479. That's how many people of that age who are unvaccinated. What's the probability that a patient who is at least 65 was unvaccinated? So 2479, those are the people who are old enough and unvaccinated. And what's the probability among people who were 65? So I want that probability out of what? Out of the people of that age group. So here my probability is going to be a lot higher because I'm not even looking at the full sample anymore. So very, very subtle difference. And I think while I was talking through that, hopefully I also answered part E. So why are the answers for part C and D different as well? I'm looking at literally the same event space. So the event I'm looking for is unvaccinated people who are at least 65 years of age. In part C, the sample space I was looking at is everybody who was part of this study. In part D, the people I'm looking at, like, you know, as like my overall sample space are only the 65-year-olds. So only the 3,247 people of that age group. And in this case, my probability is going to be 0.763. All right, moving on to question 2. All right, we have 3 coins. 2 are fair, and the other one is a cheater coin. Has 2 heads on it. So I pick up a coin at random and flip it. What is the probability that it lands heads up? So I think this is a good, by no means mandatory, but I think this is a good candidate to make a tree diagram for. So here's what I'm going to do. Basically, how many events do we have here? Or how many experiments, I guess. We can kind of think of this as being 3 different things that we're going to do. Like we're going to do 3 different experiments. So let's do this. Let's say fair coin, fake coin. I give myself enough room to develop this. Let me see. So fair coin. I have a perfectly equal chance to flip a heads or tails, right? All right. Fair. The next fair coin is very much the same, right? I have a perfectly equal chance to throw heads or tails. And finally, the fake coin. I think there's only, I don't even need to make more than one branch here. Heads, probability is 1 for all these branches. All right. I'm going to go ahead and I think there's probably a much better way to talk about this first part than a tree diagram. So let's do that. So for this first part, we're going to, I want to know what probability, I pick up a coin. I don't look at it. I don't look at what kind of coin it is, but then I flip it. So what's the probability that lands heads up? So there are 3 coins. So I pick up a coin at random. I think it's safe to assume that I have an equal chance of picking up any one of the 3 coins. So 1/3. So I have a 1 in 3 chance of picking up any one of these coins. So the first, let's say the first 2 coins are fair. If I pick up a fair coin, what's the probability that I flip a heads with it? That's going to be 1 out of 2. The second coin is, I want to give that away. The second coin is also fair. So the probability I'll throw heads is 1/2. The third coin is unfair. What's the probability that I throw heads on that one? It's absolute. That's all I can do with that one. So these 3 products I've written down here, basically I have these 2 events are independent. One is picking up a coin, and the other one is, you know, what I get when I flip it. So because of that, I can add these things together. So my final result's gonna be 1/6 plus 1/6 plus 1/3. And what do I get there? I think this comes out to be 1/6 plus 1/6 plus 2/6, which is equal to 4/6 or 2/3. All right, so hopefully it makes sense that I'm not, there's a better than 50% chance I'm going to throw heads, but it's not guaranteed. All right, part B sort of asked this question in the opposite direction. I pick up a random coin and flip it heads up. What's the probability this is the 2-headed coin? So this time I'm going to make a tree diagram. So for 2 different events. So event 1, I'm going to say that that's the choose, and event 2 is the flip. So what are the options if I choose a coin? It could be the fair coin. or yeah, it could be a fair coin, or it could be the fake coin. So what are the probabilities of those two events? Well, there's a 2 in 3 chance that I choose the fair coin, and a 1 in 3 chance that I choose the fake coin. Now I'm going to flip the coin. If I flip a fair coin, I could land on heads, I could land on tails. Those things are, I'm going to need to be consistent with my, put the result on the branch. 1/2, 1/2. And with the fake coin, what can happen? Only one thing. All right, we've built a tree diagram, but now let's do this. You pick a random coin and flip it heads up. So this right here is going to kind of this right here is going to identify our sample space. So let me get a new color, and I'll say red is sample. I pick a random coin and flip it heads up. Okay. So what branches, or yeah, like what endpoints on this tree diagram actually do I care about? Well, that's this here and this here. So those are the possibilities, right? This one here where I flip tails, that doesn't matter. That is not relevant to what I'm doing here because I picked a random coin and I flipped it heads up. So this probability involving tails, that's not what we're dealing with. All right. So the next part of this, what's the probability that, so in the condition that I flipped heads, what's the probability that it was the two-headed coin? Okay. So orange, that's a bad color. What's a good color to try here? Let's do this pink. So let's be a little more accessible here. Red is the sample. Pink square is the event. Okay. So now, we didn't even talk about it up here, but if I were to add up all these probabilities, or like all the, what do I want to say here? Actually, I'm not going to go back to that. Typically, when we find probabilities, the denominator is often, everything. So if I go back to part 1 here, for the first 3 parts of this question, the denominator was the cardinality of the entire sample space. When you deal with conditional probability, what often is happening is you're basically throwing things out of the sample space. You're making a new sample space that is a smaller subset of the giant sample you were given. That's kind of what we're doing here. And what I mean by that is this. Let me find the probabilities of all of these branches. And the way you find the probabilities in tree diagram is basically start from the trunk, whatever the metaphor you want to use here, the beginning, and multiply all the probabilities you see here. So 2/3 times a half, that's 1/3. 2/3 times a half, that's 1/3. 1/3 times 1, that's 1/3. Those probabilities all better add up to 1, and they do. So you might say, all right, the probability is 1/3 because the thing I want, the event, the probability was 1/3, right? Not really, because the probability we want to calculate is, all right, what's the probability of the event? It's 1/3. But what's the probability of the sample? It's 1/3 plus 1/3. So I get 1/3 over 2/3. So this conditional probability is 1/2. So if you flip the heads, it probably is not very intuitive, but if you flip the heads, there's a 50% chance that you picked up the fake coin. All right, that is all for question 2. All right, so question three. According to estimates, 1% of women over the age of 50 have breast cancer. And 90% of those who do will test positive for it. And 8% of women will have false positives. What is the probability that a woman, I misspelled woman, awesome, that a woman who tests positive for breast cancer on a mammogram actually has it? So this is kind of the quintessential application of Bayes' theorem here. I'm going to set up with a tree diagram. I think that's a little more intuitive, but you can use the Bayes' theorem formula as well. So here's the way I'm going to set it up. I'm going to have basically kind of two steps, two experiments here, because there are two things that are going on. A is, actually, I'll kind of frame them as questions. Does the woman have cancer? So this is kind of like reality. What is truly happening? And then, yeah, and typically A is not anything we can never know for certain. And B is what does the test say? So these are the two questions that we're going to build our tree diagram off. So what are the two options here? Yes, no. And what do the tests say? Positive or negative. So let's set up the tree diagram along those lines. So what did I do before I put the options on the branches? Okay, yeah. So does the woman have cancer? Well, either yes or no. What's the probability that she actually does? According to estimates, that's going to be 0.01, which means the probability she doesn't is 99% or 0.99. So this is A. B is all about what a mammogram indicates. So this is a positive. This is negative. So if a woman has cancer, what's the probability that a mammogram will bear that out? 90%. So if a woman has cancer and then they get a mammogram, probability of a positive test is 0.9, which means the probability of a negative test is 0.1. Okay, so, and these are conditional probabilities, and what I mean by conditional is the probability of the mammogram being positive has very much to do with whether the woman actually has cancer. And that's kind of what this tree diagram is going to show. So let's now say the woman does not have cancer. It's not impossible she'll test positive. That happens. So that's what this 8% is. 8% of women will have false positives. So if a woman does not have breast cancer, there is an 8% chance she will test positive anyway, which means there's a 92% chance that she will test negative. Okay, so this is my full tree diagram. Now, let's use this to carefully answer the question we were actually asked. So let me actually use the same colors that I used before. So red, circle, sample. Because basically what I'm doing here in these conditional probability questions is I am reducing things. I'm reducing the sample space. So let's talk about this. Okay. So what's the sample space? What's the probability that a woman who tests positive for breast cancer on a mammogram actually has it? So we're reducing the sample space, not so basically right now the sample space is all women over the age of 50. But the way this question is being posed, what is the probability of the woman who tests positive for breast cancer? So now I want to reduce this sample space to the women who tested positive for breast cancer. So those are women in this branch and the women in this branch, because they both tested positive for cancer. Not all of them have it. But those are the branches I care about. So then now I need to identify the event space. So among the women over the age of 50 who tested positive, which ones actually have cancer? Okay, so those are going to be these women here, right? Because question A is, does she have cancer? So now I have my sample space, I have my event space. Don't need all of them, but let's actually go ahead and find all the probabilities, because that'll give us a good check of something else. So to find the probabilities, I multiply the kind of starting from the beginning on the left, multiply basically all the numbers you see as you get as far right as you can. So 0.01 times 0.9 is 0.009. 0.01 times 0.1 is 0.001. 0.99 times 0.08 is 0.0792. And 0.99 times 0.92 is 0.9108. Let's just make sure if I add all those things together, they do come out to be 1. So all those probabilities add up to 1, but I don't want to know all those probabilities. The only ones I want to know are the probability of the event over the probability of the sample. So the event has a probability of 0.009. The event has a probability, or sorry, the event has a probability of 0.009. The sample has a probability of 0.009 plus 0.0792. And I get a final result of 0.102. So let's remind ourselves, what did we actually answer? So if a woman tests positive for breast cancer on a mammogram, so that's, and this is kind of a counterintuitive thing. It seems like testing positive for cancer means you have it. But in this situation, and as far as I know, these numbers were realistic when or were, reasonable when I looked them up. But yeah, testing positive, still better, a kind of a very slim chance that you have it, even if you test positive. So, and that's kind of what Bayes' theorem is meant to uncover, is to kind of show us that these, because false positives exist, there are these kind of counterintuitive results that show up when you're calculating probability. So that's all for checkpoint 10.